Now that we have the most important definitions in place, let's start actually using them for machine learning. In this video, I'll explain the maximum likelihood principle, which is a widely used technique for optimizing model parameters. I'll give an example of how the maximum likelihood principle leads to a probabilistic interpretation of least squares regression. Okay, now the premise is as follows. We're dealing with the data set of n independent observations. And we are set out to recover the probability distribution that may have generated this data set. We're going to model this distribution with a set of parameters. This distribution is called the likelihood of the data set. This is a distribution with respect to the data variable, right? Because every time I may observe a different data set, and this probability distribution gives us the probability or the likelihood of this particular data set. And it is conditioned on a set of parameters W. Now the maximum likelihood principle is then as follows. It says that the most likely explanation of D is given by the set of model parameters which maximizes the likelihood function. So let's write this out in equations. So we're looking for the set of parameters, the argmax. We're looking for the set of parameters which optimizes this function, the likelihood function. Now, I made this remark before, but I want to stress this again. This probability distribution, it is a distribution with respect to D, with respect to the data variable, but it is a function with respect to W. And that's why we call it a likelihood function. Okay, so this is what we set out to optimize. And in doing so, we're going to make some assumptions. We're going to assume that the data is independent, identically distributed, which means basically that each data point xy is independently distributed. It is independently distributed according to the same distribution. So the same distribution refers to this identically part of IID, independent, identically distributed. So our assumption is that each data point x is drawn from the same distribution, which is parameterized by a set of parameters W. Now we make this assumption because then the joint probability distribution, so the joint probability with respect to each of these data points, factorizes into this product of all the individual probabilities. And this is written out as follows. Okay, so we're going to optimize the maximum likelihood function. Now let's take a look at this thing. It consists of the product of all of these individual likelihoods, all of these individual probabilities. And these probabilities typically have values smaller than 1, so the product of all of these values will eventually lead to a very small value. So if we design numerical algorithms around this, we can expect numerical underflow errors. So how are we going to deal with this thing? How are we going to maximize this? Well, instead of optimizing the likelihood directly, we're going to optimize the log likelihood instead. So before I'll explain this, I'm going to write this out to see what we're talking about. So we're going to find the set of parameters that maximize the log of this likelihood. Now we know from the rules of working with logarithms that the logarithm of a product of all these items decomposes into the sum of their logarithms. So this is key. So the log likelihood then becomes the sum over all the log of the individual likelihoods. Now, why are we allowed to do this? First of all, I mentioned that taking the logarithm is a monotonically increasing function. It will not change the location of the optima. And I can quickly prove that this is the case. So consider what we're doing here. We're finding the set of values W that optimize this function. And we know that we've reached an optimum whenever the derivative with respect to these parameters is 0, right? If we have some function of W So this is a function of w. We know that at the optimal location, the dw of f is 0. Okay, so this is the criterion. And we're going to solve this, and then we find a value for w, and for this particular value of w, we know we are at a local optimum. Now let's consider the optimization of the log likelihood. So this tells us that we have a criterion that the derivative of w of the log of the likelihood has to be 0. Now let's use the chain rule here. Let's write this out. So the derivative of the log gives me 1 over the thing inside the log times the derivative of the thing inside the log, which is the likelihood. So this is the criterion that needs to be satisfied for optima, for optimal values for w. Now, we know that this particular term over here, 1 over the likelihood, will always be some positive value. So this will never become 0. So it doesn't contribute to the location of the optimal value for w. So we see that this is actually the constraint that has to be satisfied. So we conclude that optimizing the log likelihood gives us the same value for w as optimizing the likelihood. And optimizing the log likelihood is much more convenient because now I have to deal with a sum of all these log likelihoods instead of a product of all these small values. And this is much more convenient to work with, especially when we model our likelihood or our probabilities using Gaussian functions, as we will see soon. Now, a final remark to be made here. Typically, we consider the minimization of error functions rather than the maximization of some criterion. So the corresponding error function that we want to minimize would then, of course, be the negative log likelihood. So optimizing or maximizing the log likelihood corresponds to minimizing the negative log likelihood. Okay, so let's do this. Let's compute the log likelihood. Now we're going to model our data distribution with a Gaussian distribution. Right? We've encountered the Gaussian distribution before. We made the assumption of IID. So this means that my probability distribution, my joint distribution of x1, x2, etc., conditioned on the model parameters, decomposes to this product of x1 conditioned on the model parameters x2, etc. Okay, now let's actually compute this log likelihood. So remember that the logarithm of a product of items decomposes into the sum of logarithms. So first of all, we have this front factor over here. So that gives us the log of 2 pi sigma squared d over 2. So 1 over this thing. Plus, here we have a product of all these exponentials. So that becomes the sum I is 1 to n of the log of these exponentials Okay, so now we're going to continue using the properties of logarithms. Remember that if we take the log of x to the power a, for example, then we can move this power to the front. Now let's do this. First for the front factor term. So we recognize that we have 1 over something, so we can write it as instead as this term to the power minus d over 2, and we're going to move this minus d, the d should be an n, minus n over 2, and we're going to move the n over 2 up front, so that gives us minus n over 2, the log of 2 pi sigma squared. Now in the sum we take the log of this exponential, so these cancel each other out. So this gives me the sum over minus 1 over 2 sigma squared xy minus mu squared. Okay, so this actually looks quite nice. This is something we can work with. So what we're now going to do, we have now this expression for the log likelihood, and we're going to optimize over its model parameters. And we do so by setting the derivative with respect to one of those parameters to 0, so the derivative of the log likelihood, given the model parameters, we set this to 0, then we solve for mu, and this would give us the maximum likelihood estimate for the mean. So let's actually do this starting with the model parameter mu. So we just derived this expression for the log likelihood. Now let's write this out. This term doesn't depend on mu, so it becomes 0, its derivative. So we focus on this term. We note that the derivative, the mu of xy minus mu squared is 2 times xi minus mu. Okay, so let's use this. So it tells us that the derivative is equal to 1 over 2 sigma squared. It's a constant, it isn't affected. Y is 1, n times 2 xy minus mu. And the optimization criterion is then that this derivative has to be 0. So let's solve for this. Well, these factors 2, they factor out. Okay, so this thing has to equal 0. This thing is the sigma squared is some positive value thing, so we have to find the constraint where this sum equals 0. So solving this problem is equivalent to solving the sum y is 1 to n of xy minus mu equals 0. Now let's move this xi part, to the other side. So we actually sum y is 1 to n mu equals. So so we take a sum over some constant mu value. It doesn't depend on the index y. So actually what we're doing here, we're counting n times the parameter mu is equal to this thing. So we see that mu is given by 1 over n times the sum over all data elements. And this is known as the sample mean. So we just showed that if we compute the maximum likelihood solution for the mean parameter, we actually obtain the sample mean. Okay, so we analytically derive the maximum likelihood solution from mu, and it is given by the sample mean. Now we can also derive an analytic solution to the maximum likelihood for sigma squared. So let's do this. Now we differentiate with respect to sigma squared, and we set this differential to 0. So let's see, we first have this term. So we take the derivative of this log. So that let's write the front factor, 1 over the thing inside the log, because that's the derivative, and then times the derivative of, this is a chain rule, times the derivative of what's inside this log with respect to sigma squared. That gives me 2 pi. Then we look at this at the second term. So we take the derivative here of 1 over 2 sigma squared. So this would give me minus 1 over 2 sigma to the power 4. Okay, so let's write this out. So this minus becomes a plus, and we have 1 over 2 sigma to the power 4 times this sum, which does not depend on sigma. And this thing has to be set to 0 in order for satisfying this optimality criterion. Okay, let's again simplify this thing. So these 2 pi factors factor out. We have this 2 sigma squared over here, 2 sigma to the power 4. So we're going to multiply with sigma to the power 4 to get rid of these fractions. So we multiply with 2 sigma to the power 4. So that gives me n sigma squared plus the sum and this has to equal 0. Okay, now let's rearrange terms. So we move this part to the other side. and we multiply with minus 1 over n, which gives us that sigma squared is 1 over n, the sum of the square distance of each point to its mean. And this is known as the sample variance, as we have defined in one of the previous videos. Okay, so we see that the maximum likelihood solution for the variance is simply given by the sample variance. So given the data, we were looking for a set of parameters that would give us a Gaussian distribution, which would give the most likely explanation of the data. And we did so by optimizing the log likelihood, and this gives us the maximum likelihood estimators for the mean and the variance parameters. And we showed that the solutions were actually given by the sample mean and the sample variance respectively. Now let's do a sanity check. Suppose we actually know the distribution that generated the data samples. So suppose I draw multiple data sets. Data set 1 consists of, well, n of these observations. And I have another data set 2, which also consists of n observations. And we say that this data set is drawn from a known Gaussian distribution, and it looks like this. Now note that the maximum likelihood estimates of the parameters are a function of the data, right? I could, for example, compute the maximum likelihood solution for mu simply as the sample mean over the data points in my observed data set. So that means that every data set generates a particular estimate for the mu. Now we know the distribution where the data comes from. So we say it comes from this distribution. So we can actually compute the expected value of the maximum likelihood estimates. And ideally, these should of course coincide with the parameters of the true distribution itself. So let's check that. Let's do a sanity check. Okay, so what would the expected value be if we consider the data as my random variable? We compute the expectation over all these possible data sets for the mu parameter. So that would mean that I compute the expected value of the sample mean given over here. So let me write that out. So I can take the sum and the front factor outside. So that's 1 over n. The sum is 1 to n. Expected value over the data points of xi. Now remember that each data set gives me a particular value for xy, and all these data samples xy are identically distributed. So what I'm computing here is 1 over n, this sum y is 1 to n, of the expected value of these data points, where each data point was drawn from the same distribution. Well, and the expected value of this thing is given by the model parameter mu. So we see that we are actually computing the mean of mu, which is simply mu. Okay, so this is good news. It means that if I observe all of these data sets, then the expectation over all these data sets of my maximum likelihood estimator actually gives me the true mean. So that actually means that that the bias of the X estimator is 0. Here I note that we call the bias of an estimator the difference it makes with the true value that it's trying to predict. And in this case, we have 0 bias, so it is an unbiased estimator. So now let's also do this sanity check for the variance parameter and compute the expected value over all my data sets of this maximum likelihood estimator for the variance. Let's rewrite it a bit by moving this term to the front. I already did some pre-computations to speed things up, so there it is. And this term, and let's also expand the quadratic form in here. So that tells us that I'm going to need to compute the expected value of these 3 separate terms. Again, making use of the linearity of the expected value, I can split this into computing 3 separate expected values. And I take these sums outside. Now, this term consists of all these expected values of xy squared xy, xn. Now we actually have a way of computing these expected values. We've seen them before. Namely, we've seen the term the expected value of xi squared in the definition of the variance. If I take the variance of xy, or differently put, I compute the covariance between xy and itself. This is given by the expected value of xy squared minus the expected value of xy and this thing squared. And we know that the variance of my random variable, which is distributed via this Gaussian, is given by sigma squared. We also know that the expected value of xy is given by mu, so this thing over here becomes mu squared, and this tells us that the expected value of xy squared is given by sigma squared plus mu squared. So let's write this. Let's mark this down. So the expected value of xy times xj in the case of y being equal to j is mu squared plus sigma squared. Okay, now let's make some space. Let's put this aside so we remember where it came from. Now the expected value between of the product of two random variables can be derived from the covariance. So let's do this. So the covariance between xy and xj is given by the expected value of xy times xj minus the expected value of xy times the expected value of xj. And we know that this covariance is 0 because all the data points were independent. These random variables were independently distributed. But they were distributed with the same distribution, which had an expected value or a mean mu. So this tells us that the expected value of xy, xj is given by mu squared. So let's mark this down. The expected value is mu squared in the case that y is unequal to j, because then we're dealing with two independent random variables. Okay, now let's make some space. We move this over here to remember where we got this expression from. Okay, so let's write this out. We have 1 over n, the sum over all these i's. The expected value of xy always gives me mu squared plus sigma squared. Then we have minus 2n times, then if we look at this thing, this is a sum over expected value, and so it will generate a mu term for every item in this sum. So we have n times mu squared, but only when I is equal to j, so only when this I equals this n, and this happens only one time I get this sigma term in it, so we have plus sigma squared. Okay, so those were the items in this particular item. And we do this also for this one. So we have plus 1 over n squared. And then in this entire sum, I get over n. So I have n squared times I encounter the term mu squared, but only n times I count sigma square. Okay, now let's collect terms. First of all, I would like to note that this entire sum does not depend on the index y. So this part is just taking the average, so it can be omitted. So we see, let's see, we have these mu terms cancel out. And we have sigma squared. We have sigma squared minus 1 over sigma square. And this equals n minus 1 over n sigma square. Okay, so we see that if we compute the expected value over all these data set of my predicted variance, of the maximum likelihood prediction for the variance, I actually obtain that it is given by a fraction of the true variance. So my predicted variance is slightly smaller than my true variance. So this means that I have a biased predictor. Okay, so this is what we did. We modeled our data. We said that our data come from this Gaussian distribution, with some mean mu and variance sigma squared. And then we looked at what the expected value would be of my predictors, of my maximum likelihood estimates. We showed that the maximum likelihood estimate actually gives an underestimation of the true variance. Now, we could of course define then an unbiased variance estimator that corrects for this term, given by n over n minus 1 times our maximum likelihood estimator, which would then be given by 1 over n minus 1 times the sum over each squared distance of the data points to the mean. And now if I were to compute the expected value of sigma tilde squared, I would actually obtain the true variance. Okay, so this would give me an unbiased estimator of the variance. Now we can gain a bit more intuition for how this can happen. So let's say our data comes from this green distribution over here, and we sample 2 points of it. Let's say these 2 blue points. Well, then I can make an estimation of the distribution, and it will probably look something like this. So I'm fitting a Gaussian to these 2 data points, and the average of the Gaussian is corresponding with the sample mean, and the variance corresponds to the sample variance. So I have this actually an estimation of the true variance, but still, this is the best fit I can do. Now, if I were to sample again 2 points and make my estimates for the average and for the variance, I would get this best fitted or most likely distribution that explains these data points. And finally, if I do this a 3rd time, I would maybe get these 2 data points sampled, and my sample mean would be over here and my variance over here. Now, if I were to compute the expected value of the means, then I have a mean over here, here, and here, and the mean over all these maximum likelihood predictions for the mean would then correspond actually with the true mean of the distribution. But if I would take the mean over all these variances, I would take the mean over all these small variances and would get an underestimation of the true variance.